Okay, thank you so much again. We'll continue with our chapter 3. Unfortunately, we can't do face-to-face, but nevertheless, most of the important equations that we have done before stands. It is more into summing up some graphics, some depth understanding with the engine system in coming, I think, lectures that we want to see. But more importantly is that to understand the physical meaning of it, why actually we are doing this. Second thing, to also to understand how those parameters that we have learned in the previous lectures interact each other or depend each other. So that we will see in this particular lecture. I remember we stopped in optimum expansion condition the last time. So I will continue with this, and once we have completed in this chapter 3, then I think you'll be more than prepared to do a very basic exercise. I mean, our first exercise, which is going to be tomorrow. So today I think we will complete that lecture, and then we can move on to the actual exercise tomorrow. Alright, if you look at optimum expansion condition, now the most important thing is we have learned that you have pressure ratio, which is very, very important. You have surface ratio, which is important as well. Then we have also the epsilon, which is CP/CV ratio, which is related to the actual fuel. So if you look at this particular graph, it tells you basically how we can get a very, very good high coefficient. That means the thrust coefficient. The higher that actually you have is better. Now there is always the design parameters are important. So when you look at it, what this actually graph tells you that a good POPE, the internal engine pressure with respect to external pressure, which is the ambient pressure normally, the higher it goes, it looks like actually produces a better, it gives me a better coefficient. But unfortunately, we can't have so high because of the design and the constraint of technology for today. So there are ranges of PO ratios that we have seen in this graph, and what we see is that we have to look into the actual expansion ratio that we have. That means the surface ratio, which is epsilon. So when you look at it, it seems that the higher surface ratio that actually you have, it seems to be quite positive. But don't forget, when you go higher surface ratio, which means that finally your expansion becomes almost, there's no expansion. That's what it means. So this is something, a condition that you don't want to actually have in that sense. Reason being, if you have those kind of conditions, then your PO has to be very, very, very high to compensate for those kind of conditions, which we can never achieve. So what I'm saying is that you can never achieve a PO which is infinite. That means as much as you want. No, we can't do that. So there is a limit to this, the PO that actually we can achieve. So therefore, we need to actually optimize in terms of the actual surface ratio. Now we have understood also that in order to the actual surface ratio that we want to optimize also helps us in order for us to achieve a higher thrust, which is the CF. Okay? That we have also shown successfully in the equation that we have. So now if you look at it, well, too high of a surface ratio might not be actually also achievable, because then it becomes, expansion becomes too much, as I've said just now. So we will fall probably somewhere here, but in order to stay in a very, very high condition, that means a very, very high thrust, technically speaking, you need to also look at your exact POPE. So let's assume that actually somewhere here, but now what is more interesting here is this. Now your kappa, CP/CV ratio. The CP/CV ratio is also seems to be very important. Now if you look at it, a higher CP actually will produce a better coefficient, because kappa is a CP over CV, right? So if that's the case, we say that if you control, if you actually have a controlled pressure, it is not going to give you a good thrust. So practically you can actually control the volume, but you need to actually evolve. You need to let the pressure actually evolve. So therefore, when you have actually a smaller kappa, then you should be actually having a good thrust coefficient. So this is important to understand. Now, it doesn't always mean that you can achieve a very, very high POPE. Alright, let us actually now take an example. I'll pick one kappa. Here is let's say kappa 1.2. Let's see in our second slide here. In your notes, alright. Kappa 1.2. So let's see. Now this is quite interesting. If you look at it, cross section AEA throat, with respect to the throat, basically you still have the epsilon. Now, and the class coefficient. Now, what exactly happens? As I've said, so when your surface coefficient, basically cross section ratio actually increases, it seems that it is quite positive. It's quite positive. So does it mean that we can keep on actually increasing the cross section ratio? No, it is not. Just like the example that actually I've given you just now, which is basically the pressure coefficient. We can't keep on increasing to infinite. So likewise, this is just giving you what would be probably optimum. So now, with respect to cross section ratio, what we have here is basically we have now the pressure ratio. So we have plotted, for example, pressure ratio 10, pressure ratio 20, etc. So now if you look at it, the graph goes this way. The graph goes this way. So practically when the graph goes this way, you want to pick the highest point, which is the maximum point. So once the maximum point of each and every single parameters has been determined, you can have practically a line. This line is plotted with respect to the maximum peak of each of those ratios of pressure. This has been plotted. Now, this is optimum. If you look at what is optimum, is we assume that the exit pressure is equivalent to the atmospheric pressure. So as I've said, atmospheric pressure is what, 1 bar, for example. Now, what happens if the pressure actually drops? So this may also start varying. So we can see that you have a curve fitting method. We drop this. We hope that this is going to be actually dropped accordingly. So a graph fitting is done to determine a minimum level. So you see this is a minimum level, dotted line that I've plotted here, which I call it a solution. So it just gives you this range. Now, if you look at it, this is just that engine can come in a different manner. What you need to calculate first, basically, give me the ratio. Give me that actually ratio of surface, give me a ratio of pressure, then I can tell you what actually CF you can produce. So that's what it means. So different launches may have different parameters altogether, but you will find what actually they're supposed to produce. Right? Important, you understand. Again, the take-home message would be, you cannot simply increase these ratios. There is a limit to it, but it gives you basically information how they come into the play, how they are actually interrelated. Let's see the next slide. This will be a bit more interesting in terms of, look at the cross-section ratios. Okay, now here what you see, the actual performance. Now, as I've said, the ratio we start. Let's say the ratio is practically nothing, 0. So you have somewhere infinite there, alright? Then you start having the ratios. What ratios? Basically the pressure ratios. Okay. Then we start plotting in accordance to the pressure ratio. What is more interesting, if you look at this, when you keep on increasing the cross-section ratio, it looks like your thrust is going to be actually drops. It is true. Because if you, as I just now mentioned, if you start doing this maximum, you just keep on opening up, practically there is no expansion. When there is no expansion, it doesn't actually respect the rocket equation that we talked about. That means we need to have the jet flow. You're not creating the jet flow. So this is what we say the impact line. Why impact line? After this, it doesn't make any sense anymore. So it's like a dead zone for us. So we should be operating somewhere in this region. Okay? Again, same. In every curve, you should be able to find a maximum point. So we plot peak. So you tell me what is your engine, you tell me what is your cross section, and you tell me what is your operating pressure. I can tell you exactly how much of thrust that actually you can produce. Don't forget, this is the actual output thrust that you have, and this is basically the thrust, convergence thrust. That means what? When the fuel goes into almost the throat and almost want to come out of the throat, and this is at that point. So it is inside the engine with respect to the outside of the engine. This is the actual that you want to have. So which means that if you have a flow, let's say you have a gas flow into the throat, do you want the same amount of flow, or rather same velocity to be out? No, you want more. That's what it means here. So all what we want to do is that we have to make sure they are not the same. If they are the same, practically what you are saying, that the convergence and the divergence forces are still the same. So that is not idea of designing an engine. In fact, we wanted to do design an engine because based on what we need in the rocket equation, we need to have the convergence force, or rather convergence thrust. It should be actually much smaller compared to the actual force that is the rocket is going to experience. So we can achieve by doing so. Okay. Now this is quite interesting. We talk about the flow and we talk about the nozzle. Now what you see in this, this is an experiment done. What you see in this actually slide is that other uncommon conditions. Uncommon condition, there is so many questions you can ask. For example, what happens if my expansion is below expansion? That means what? I don't expand. In fact, I create just like a convergence. What exactly happened? So this gives you practically the pressure is very important. Remember, pressure and with respect to the gas flow in terms of Mach number. So you can see all these are technically unpopular, or the one that actually you can think or you can ask, what happens if my Mach number less than 1 up to here? Why not? It can happen. What happens if my Mach number is below 1 up to the throat? But it is not common. It is not common. Okay, but these are the questions you are. What happens if I do a over expansion? That means what? I go in, do a expansion to over expansion, so to say. What happens? I have a symmetric. What happens? All these are actually something that for you to think and for you to understand. But again, these are the unpopular ones. We are not actually flying the rocket with these kind of solutions. No, it's just a solution for you to understand what happens if this goes bigger. Let's say my cross section goes bigger or smaller, or my Mach number of the actual exit gas goes below Mach number 1, and sometimes you can actually enter even inside up to the throat. The gas is actually so slow. What happens? What exactly happens? All this is actually given in terms of the pressure and the velocity. But remember, this stays. This stays. Why? Because when there is no combustion, basically there should not be any gas flow. So this is your inside. Once the gas flow starts, then it should start going up. So if you look at it, EFG looks like it has produced a positive flow. High. EFG. Now this is quite common. Why? Because even, you see, there is these conditions are basically same, not governed by the Mach number. So technically speaking, you have an ambience. So assume that you produce in the engine, you produce a good pressure. Technically, you should have a flow which is high. Okay. Now this actually respects. Maybe go 3 or 4 slides before, please. There's a go on. This I think I've done before. Go on. There's one. Go on. A graph. One graph. Yeah. There you go. Remember this. Pressure. This is ideal. This is what you want. This is exactly what we want. But when you start playing around with the nozzle, when you start playing around with the cross section, and you start playing around with the exact exit pressure, exit velocity, for example, then go back to the graph just now. then this happens. So this is not very desirable, right? Correct? It's not desirable. Even this is not optimum, but at least producing reasonable Mach number. But don't forget, we need to optimize this. When you want to optimize this, that is the graph which I showed you last week. In fact, 2 weeks ago, in fact. Pressure high and drops, and velocity of jet 0 goes maximum. So, and they cross in throat. Yeah, they cross in throat. Okay, go on. Alright, divergence. Now this is important for you to understand. Coming back to, so you don't want divergence, what exactly happens? This will be quite symmetric. Right? Straight like a pipe or a duck. That's it. Now what is important here? Why we want divergence? So when you want divergence, that means there is a duct here. Let's say assume that there is a duct here and there is a duct here, right? It's just like a pipe. So instead of having a duct, you are pulling it so that it becomes like it has a divergence. So don't forget, when you have divergence, there is also losses, because the flow here, it is not parallel to the axis. Okay? Obviously you will have the losses because it is the loss of angle for sure. And here I have also given you what are the angle, typical angle, and what are the losses basically. Okay? When you have a zero angle, practically there won't be any loss. When there are angles like this, there is zero angle, there won't be any loss, because look at this component. But when now that basically it is down, or rather it has a divergence, you should have losses. But never confuse. Never get confused. These losses that you have are not the actual, it is not actually a negative loss, I would say. Remember, if this was just a duct like this or just a pipe, these losses don't exist, you know. But what we have done, what exactly that we have done in rocket is this. Instead of actually having just a pipe like that or a duct, we have just opened up the exit. So when you open up the exit, what exactly mean? There is an extra area that you have brought in or introduced. Although this area, the flow, it is not as optimum as the center, but it adds to the whole flow. Instead, your flow is this, you say there's just a duct, just only this much. Now the flow will become bigger. Obviously, you will have losses here. The strength of the flow is still middle, but you have added some extra flow in peripheric. If you don't open this up, this is not additional. It is just this that you will have. So what this tells you, yes, there is this losses here. But this losses is a positive, although it's losses, but it adds positively to my actual flow. Otherwise, I will have only one flow, just like that. So please do mark that this is not negative to the actual jet flow. It is lost, but it is added back as a positive component for the actual jet, total jet. Okay? You can't have, unless you want, if you say, okay, I don't want this, I want this much of flow, what I can do, another one I can actually open up the throat. I will have the same amount of flow, but then you go back to my graph on design on surface ratio, it is not going to give me a good CF. CF will be actually down. Period. Okay? Alright. Now, how actually the divergence loss is being calculated is just that I'm giving you an example how it is done. Now, more importantly is this. I have the same formula. As you know, this is actually, I just repeated this. Same trust formula that I've used, but don't forget, this is with respect to the actual surface. Now, the surface area here will be this. Now, for your throat, what is the difference? Is that for your throat will be, this is actually diameter of the throat. But for your axis, it will be a diameter of the axis. So, depending how much that you open up, that would be exactly your exact amount of surface outside. So you do integration, practically you should be arriving to the exact lambda that I have calculated just now. This is just for your information, as I told you again. Okay. Answers or rather the actual calculations done here. So you want to know how I calculate the lambda? Then the lambda is actually given to you. It's for your information. Go on. All right. So look at this. This is what I've been explaining just now. The best is this core flow. We have the maximum WE, that means exit velocity. But here it becomes actually is lesser. Correct? But you will have a profile which respects this. At a certain core, there is a core flow. When you come out as a core flow, then actually start dropping. That means that it start actually losing. So only the core flow here has the maximum. The rest are basically, you can imagine it is like supporting. But again, although there's losses here, it is still added to our jet. Alright? Okay, energy losses. So if you look at it, there are so many losses actually in the rocket engine. Don't forget, in your rocket equation, no losses is ideal. But when you look at this, so many losses. That is the reason the exact delta V. Remember, I always say that okay, you have WE, exit velocity, that you calculate through experiment, through the engine testing. Then after that, you have effective exit velocity. Effective exit velocity is the exact velocity is pushed out during your flight. And why it becomes lesser? This is the reason. Starting from thermal losses is great, quite a lot. Heat loss at nozzle wall is about 2% of the actual performance. That's a lot also. Highly depend on the engine property. So it's this nozzle is basically, that means nozzle. Design of nozzle is important. Very, very important. Okay, design of nozzle. Then you have a Reynolds number, for sure. The flow. The flow is important. That is very, very critical for us. And that we have also shown in terms of the Mach number that we have. Cooling methods, how we want to actually cool. Too much of heat. Now regenerative means, I think one of those lectures I've told you, we can actually heat up, especially on the nuclear engines, we can heat up the fuel before we burn them. So this is one method. Ablation, we will learn ablation is burning up the material, for example, to reduce the heat. We will learn that through re-entry. In a re-entry chapter, we will learn that because your capsules, re-entry capsules, are actually using this method basically. Then you have radiation. Radiation is typical. The only way, if you go to space, the only way that you can lose heat is basically through radiation. Okay. Then you have transpiration. Then geometry of the nozzle, just like what we have discussed. And there are a lot of chemical losses. This is actually happens in the engine. Obviously, when we have incomplete reaction, this is actually the quality of the fuel that you're going to inject in. Later, I will also share the typical fuels that we use. Influenced also by high temperature, and high temperature means what? Very, very high temperature during the combustion is also going to actually heat up the engine parts. So therefore, all is affected. Too high temperature. High temperature is good because you can use it to heat your fuel. But don't forget, it is going to affect all the other components of the rocket. So many losses are there. Go on. So if you look at it, stage 3 in Ariane, so what kind of losses I have? Okay, burning loss, 1%. Example, for Ariane, wall loss, thermal radiation loss is up to about 29%, kinetic loss, and all these actually you can gather, and you will have the actual total loss that you can calculate. Now, if you look at it, there is so many components, there are so many venues that you are going to actually lose the efficiency of the rocket. But well, you got to live with it. It's just that we got to keep on actually producing good quality engines in order to compensate for this. All right, go on. All right. Now, if you look at nozzle losses, what I'm doing here, classification, bigger chemical means what? Engine. Bigger chemical engine, smaller chemical engine, nuclear thermal engines, electrical engines. All these are types of engines. Then you have all these losses. Now, importantly, if you look at it, divergence loss is quite critical. Okay, divergence loss is quite critical. Otherwise, look at environment loss is quite small. All these others are quite small. Okay, now why divergence loss is so critical? Because this is going to affect your jet flow. As simple as that. The rest are basically at a 1%, 2%. Now, what exactly this means that usable performance on applied power means to say when you put in the amount of energy into the rocket engine, probably up to 40 to 70% is what actually is usable. Another about 30% is going to go off. Now this is very significant. We can say this strongly for a bigger engine because we can calculate that clearly, especially on the divergence. But for a smaller engine, you don't see much. We can't actually establish the exact loss because the divergence are also small, very small engines. Very, very small engines, okay? Otherwise, nuclear is quite big, we can actually estimate. And this is not typical. I think you better, maybe if you have notes already downloaded, better actually, this is not typical. The typical examples that we are going to actually use or we always encounter is basically this one, bigger one, okay? Bigger chemical engines. Because smaller chemical engines, well, it's not really effective in fact. Smaller chemical engines, if you want to have a smaller engines, might as well actually look into the options of electric. Electric engines typically, just generally you can remember this. Engine means nuclear engines will be big. Chemical engines will be big. You want a smaller engine, you must actually start looking into electrical engines. Remember, electrical engines, you don't have a very special combustion needs. Different methods are actually used. And you don't have to actually have a huge amount of storage of fuel and for oxidators. You don't have to have that. Okay? Go on. Alright. Reactions. Typical. This is quite typical what exactly happens in chemical engine. I think the chemical formulas are quite clear for you guys. Now this is just to give you what kind of a delta WE max actually I can achieve with those kind of actually action or reactions. Okay. Beryllium, I think BE, you guys know beryllium. You use boron. Aluminium is very this is quite typical. Aluminium is quite typical. Later in solid boosters or solid propulsion system, we are going to use aluminium as well. It's quite common. Ferrum, okay. Ferrum and magnesium is also quite common in that sense. So these are the typical ones you use. What I want to show here, I've listed out whatever is available. Okay, whatever is available, I've listed out. What I want to show you here, there's not much of actually difference. Correct here, this is actually 5,000. Okay. All more or less is the same. They are producing. So there is no one particular material that we have, or rather fuel that we have, is producing way beyond other solutions. No. So now the question is that if my fuel is more like same, that means what? My CP/CV would be more like similar in that sense. What can I have? I may look at the design of the engine itself. How am I going to actually optimize the design of the engine? That's what actually we need to do. And for that we have all those formulations and formulas. Go on. This is liquid fuel. So liquid fuel, remember, please do understand, when you talk about fuel, especially chemical, when you talk about fuel, then you should have also oxidator. So there's that component. So what you see in this actually slide is that only fuel. Technically speaking, this is useless without oxidator. So you should put them together with an oxidator, then it will burn. So you can always imagine, that is the reason if you look at in our design of that engine, there will be always actually two basically tanks. One is basically the fuel, another one is oxidator. So hydrogen can be also very good fuel. This is most of the modern rockets are using hydrogen, but this is a supercritical state, liquid state. Then you have, this is okay, quite typical, hydrazine, very conventional fuel, until today it's been used as well. The others are, I'm going to, okay, please mark hydrogen, please mark hydrazine, please mark dimethylhydrazine. This is unsymmetric hydrazine, okay, popular. And this is the final one, also hydrazine, but this is actually monomethyl, MMH, okay. You can find this in most of the, quite typical, MMH is quite typical in satellites. You can find them in most of the satellites that's flying now, they use MMH as a fuel. So what we have given you here is that cryogenic stage. See, out of this whole this, there's only one in supercritical state, which is the hydrogen. That means, what it means that hydrogen will be now a liquid form. Will be in a liquid form. That means it's a supercritical stage. So you can see, imagine how cool is that inside. Okay. The rest you can practically, the rest are quite similar. It's all in the fuel state. That means a liquid state. Okay. Only this one is quite, critical to look into. Then the rest of the parameters actually I've also given to you. And look at this. This is quite safe. The boiling, and then it'll be safe basically. Although you have a heat, a lot of heat, etc., it is not going to actually cause you any problem. So almost as long as we don't mix with this oxidator, which is the oxygen, it's all safe more often than not. The rest you have to actually, take care of the exact temperature inside. Okay, go on. Alright, this is oxidator. Now you will marry hydrogen with oxygen for sure. So this is also supercritical stage, which is in the liquid form. Very popular to be used. Then there are, and another one is this. This one is very, very popular. All those actually hydrazine that I've mentioned to you, more often than not they will use nitrogen hydroxide, N2O4, as their oxidators. It's also quite okay to handle, but all those high amount of actually thrust rockets that you see will be using hydrogen and liquid, hydrogen liquid, and then oxygen liquid as their fuels. Okay, go on. Okay, if you look at solid fuel and solid oxidators, so if you look at it, composite. This is the fuel that you have, composite. You have PE. This is very common. PE is very, very common. PB is also common. Polybutadiene. Well, it's also not very expensive. But remember, most of these combinations are heavily mixed with, more often than not, aluminium. A lot of aluminium. If you look at most of the launch site, you have a lot of traces of aluminium, especially when you start functioning the second stage. That means what? The booster together. Okay, second phase together. So more often than not, you will have a lot of traces of aluminium because of this additive. So this is quite typical. You can mark here, guys. Aluminium is very, very common. Let's say polybutadiene with aluminium mixture. Then the oxidator. Oxidator, you will have either ammonium-based oxidators. So these are the typical ones that you have in solid boosters. Now I haven't done a solid booster or rather solid propulsions exercise. We will do it in class. There is one equation, very famous equation that I need to introduce, Rock-Woodville equation. It's very straightforward. We will do that as a lesson, or rather as an exercise in coming classes. Okay, move on. So if you look at combination of solid and liquid fuel oxidators, don't forget, remember I told you in your exercises, the difference is that we have done the exercises and you've been exposed to all those actually phases, phase 1, phase 2, phase 3 rockets. And you know that there is words like solid booster, there is liquid engines, etc. But we want to actually know how basically this can be combined for sure. And in this actually engine, third chapter or other engine lessons, then you can see how we can actually combine. So fuel. Now, if you have the fuel, if you look at a rocket, your fuel is liquid Then you have an oxidator, so you call what? Liquid fuel engine. Okay? You have a fuel, solid as a fuel, liquid as an oxidator, normal hybrid engine you call it. Don't forget. Then you have a fluid, solid, or rather, well, you can say it's also liquid. Then you have an inverse hybrid engine. We will see how this is done. Solid and solid, this is actually solid fuel engine. Now, important, this is the what we have done in exercise. Liquid. This is very typical, very common, very popular. All those space missions that actually you see today, especially Earth-oriented missions, liquid solution. The one that you have done in your exercise is liquid, and this one, solid liquid. Solid liquid basically, because your booster, remember, your booster is basically solid. So you have a mixture. Go on. I think that's all for the chapter 3. I think we have covered most of the thing. More importantly, the equations that actually we have treated in past lessons. What is actually needed? Have a look at this lesson again, maybe for tomorrow, which is Tuesday, 11 to 1. Then I expect you to start actually doing the exercise, the first exercise for this chapter, which is already posted in your Putra Blast. I think you should be able to do it within the group. I think first assignment is not so difficult. So once you are ready with the assignment, next week what we are going to do, we are going to actually discuss your solution. And next week everything goes on well. Let's say we can have the face-to-face classes. We will start with maybe start discussing if you have any questions regarding this chapter. If not, we can proceed to the new chapter. A new chapter will be posted. I think will be posted maybe today. This week. Look out for it. Stay healthy, and I'll see you next week. Thank you.